What is additive manufacturing? Definition, types, and trends. Creating an item from thin air may once have seemed like science fiction, but for today's manufacturers, it's not only a possibility, it's become a critical component of their workflow. Bringing parts, difficult to build items, and entire products to life on demand is now a reality thanks to additive manufacturing, a process that uses software to translate a digital design into a real-world item. What is additive manufacturing? Additive manufacturing describes the manufacturing process that uses technologies to create 3D objects by adding material through an automated process. It's achieved by adding layers atop layers by depositing material, hardening material, melting a powder, or binding a powder. Some may even consider the term a synonym for 3D printing. Technology such as additive manufacturing software is being rapidly adopted among the automotive and transportation, aviation and aerospace, and medical industries and is creating everything from prototypes to finished products. Due to this, the additive manufacturing market is poised for explosive growth and is expected to reach a value of over $93 billion by 2031. Additive manufacturing has potential applications across other industries as well. Manufacturers have realized it can streamline production, build items quickly, and have better traceability throughout the entire manufacturing process. Ensuring additive manufacturing is fully integrated with existing manufacturing systems will remain a key task for manufacturers for the foreseeable future. Additive manufacturing versus subtractive manufacturing. As previously stated, additive manufacturing creates 3D objects and models by building them layer by layer. This is unlike a traditional subtractive manufacturing process, where the material is removed or part forming like forging. Subtractive manufacturing helps construct 3D objects by cutting away material from a solid block, most typically done with a CNC machine or computer numerical control, which is a shop tool device that can read computer programming inputs. Additive manufacturing. Subtractive manufacturing. Useful for rapid prototype development. Useful for prototypes requiring living hinge components. Computers and 3D printing to create products. Computers and robotics to assist standard machining processes. The finished process leaves a rough surface that needs sanding. More proficient at smooth finished surfaces. Handles intricate objects easily. Intricate shapes can be difficult. Best used for small items. Best used for large volumes of items. Primarily used in plastics. Primarily used in metals. A more slow process. A rather fast process. Overall inexpensive. More expensive overall. Different types of additive manufacturing. Manufacturers have implemented technologies through 7 different additive manufacturing processes: powder bed fusion, vat photopolymerization, binder jetting, material extrusion, directed energy deposition, material jetting, and sheet lamination. Each method is achieved through a different variation of 3D printing technology, which varies based on material state, sources of light or heat, print axis, feed systems, and post-production processing. Powder bed fusion, melting powder to fuse particles together. Ideal for most types of manufacturing. Vat photopolymerization uses a liquid instead of a powder or filament in its build platform and is a light-activated process. Ideal for Lauren injection molds. Directed energy deposition uses highly focused thermal energy delivered via laser, electron beam, or plasma arc to melt and fuse material. Used exclusively in metal additive manufacturing. Material jetting, tiny nozzles dispense droplets of a waxy photopolymer layer by layer, which is hardened via UV light. Ideal for items requiring high detail and high accuracy. Binder jetting, similar to material jetting, but rather uses a powdered material and a binding agent. Primarily used in furniture design models. Material extrusion, a thermoplastic filament is extruded through a heated nozzle onto the build platform, which solidifies as it cools. The most commonly referred to additive manufacturing method when someone is discussing 3D printing. Sheet lamination, ultra-thin layers of solid material are bonded by alternating layers of adhesive. Best used for non-functional models. Benefits of additive manufacturing. The power of additive manufacturing makes it possible to build parts or structures that are impossible to manufacture through traditional methods, enabling rapid prototyping and the creation of new or replacement products that were once considered impossible. Companies are being very strategic in selecting which parts can be better produced through additive manufacturing, says Ron Belts of Bustreak, an MES solution provider. Using additive manufacturing lets companies create parts quicker and at a lower overall cost, giving them a huge competitive advantage. To maximize that advantage, it's crucial for manufacturers to determine the right additive manufacturing software solution that fits into their production line. On an industrial level, this means integrating the capabilities of additive manufacturing software with an existing manufacturing execution system, MES, or quality management system, QMS, to print, machine, inspect, and fabricate parts quickly and with fewer non-conformances. Because manufacturers must often adhere to specification requirements and guidelines when creating parts, it's critical for the AM process to ensure specifications are adhered to and that the process itself is auditable and repeatable. As such, information and data must be managed in real time and integrated with other systems to give production managers and quality managers the resources they need to drive the continuous improvement process. Using software for additive manufacturing. The software used for additive generally involves 4 steps, according to Eric Miller of Partha, a provider of 3D printing products and services. In the repair process, the repair of solid model geometry makes a watertight solid. During build preparation, the support material is generated and parts are oriented and packed within the build volume of the AM machine. With the slicing and tool path, cross-sections of each layer in the vertical build direction are used to calculate the tool path or deposition pixels for the deposition head, laser, or jets. Using machine control software, the programmed tool path or deposition pixels are executed to build the part. Many additive manufacturing software solutions can carry out these capabilities, but it's the integration with MES and QMS systems that can truly differentiate and control an AM workflow. MES and QMS systems can help reduce waste, track builds, and maximize production, thanks to the enhanced management of non-conforming scrap parts, advanced serialization functions for multiple parts with different serial numbers, and the flexibility to track real-time combining of parts to optimize the routing of work on the production floor. Organizations are going to need their MES QMS software providers to give them the capability and functional components they need to have better control, detailed audit trails and documentation, and the ability to ensure compliance, Belts says.